All right, perfect. Thank you. That was a great talk, Zach. So as we've all just heard, there's an array of analog activities going on to support crewed activity on the surface of planetary bodies under the Artemis program. These simulations are invaluable for assessing how deployed instruments function, how to operate them effectively, and how to use their data products. So next slide, please. So in this presentation, I'm going to share some of the results from our remote in situ and synchrotron studies for Science and Exploration 2, or RISE 2 field campaign, where we tested the utility of a portable infrared thermal hyperspectral imager, or HSI. And we did this across 4 different simulated EVAs. Our goal for this was to understand how an HSI could support real-time mineral identification and guide some sample collection. So next slide, please. Before I dive into the details of this, I did want to provide a brief overview of the scientific reasoning for why we would want an HSI during an EVA. So hyperspectral imaging is actually a very powerful tool that can provide information about the surface's reflectance and emitted radiation across many wavelengths. The advantage of this is that HSI can identify our compositional information for both visible and most importantly invisible materials on the surface. Prime candidate for HSI is actually the detection of volatiles on the moon, for example. The bottom image here is taken at Meteor Crater with an HSI, and it shows just how much detail is in these instruments can reveal, and not just about the rocks that are around, but also outcrops that are farther away and terrain features. Next slide. So to test the utility of an HSI, the RISE 2 team conducted simulated EVAs at Kilbourne Hole in New Mexico with 4 analog crews. The image on top is a subset of the team. Some of them are, or actually both of them are our chairs today. And the bottom image is actually of each station that we did these simulated EVAs. So each station, we had 3 stations, and each station was further split into 2 substations. At substation A, the analog crew conducted an EVA without any instruments. But at substation B, the crew had access to 4 different field deployable instruments, including the HSI, but also an XRF, a ground penetrating radar, and a LiDAR. So the purpose of these 2 substations was so that we could compare the scientific return of the EVAs with and without instruments. Next slide. So clearly for this talk, I'm going to focus on the HSI. This is the instrument shown here, and it is a thermal hyperspectral imager built by Spectrum Photonics in Hawaii. It operates from 7 to 14 microns and provides emissivity and surface temperature data. We utilize the HSI as a standoff instrument that would be mounted on a lunar terrain vehicle, for example. The analog crew, therefore, did not have to set up the instrument or run the instrument. They simply chose the location and seen that they wanted the HSI measurements, and then received the process data once the measurements were complete. For this simulation, we used a standoff distance of 10 meters, which resulted in a spatial resolution of about 10 millimeters. Next slide. So this is an example of the data product delivered to the crew, and is actually one of the scenes selected by one of the analog crews. It includes a visible context image, a false color IR image, and then 2 mineral maps on the bottom. The mineral maps display 3 different minerals per map based on what we expected and knew to be present at Kilbourne Hole. These helped the crew identify both representative and unique sample targets. Additionally, the HSI data products guided analysis with an XRF, and also confirmed our compositional analysis with the HSI and also crew geologic knowledge. So in the top mineral image, you can see that there's a few rocks highlighted in quartz in red, a mix of quartz and plagioclase in yellow, and plagioclase in green. In these data sets, the blue in the top mineral image is likely due to noise from strong temperature variations. In the bottom image, you can see some olivines in green on the right-hand side of the image. Next slide, please. So one clear takeaway of our simulations and was mentioned by the analog crew, is that 65 minutes of true training that we provided prior to the EVA simulations wasn't sufficient. This result wasn't unexpected and certainly isn't reflective of how astronauts would be trained for real. The real lesson here, though, is that for future analog studies, to make sure that the analog crews have thorough training on both the instruments and their data products in order for the simulations to be high fidelity. Still, the crews did find that the mineral maps were valuable. The mineral maps helped prioritize which rocks to collect for further analyzation with the XRF and which samples to skip because they had already found something similar. Some challenges that the crew had, though, are translating the 2D HSI imagery into the 3D field environment. So this photo series illustrates that challenge a little bit, where the top left image was taken from the perspective of a crew member with their phone, while the right panel of images is from the HSI. And so I tried to put some symbols on this image so that you could see how what points on the HSI align to the points in the context image from the point of view of the astronaut. And you can see it's kind of difficult to tell how to translate the 2D to the 3D. In some cases, to compensate for this, one crew member would physically stand in the scene and be directed to a sample of interest by the other astronaut who was standing at the HSI location. To further improve this, one could consider using an eye-safe laser to highlight targets directly in the field, or as Zach was just talking about, augmented reality would be great to take HSI data and overlay it onto the site that you're looking at. So next slide, please. So what are our recommendations? First, obvious recommendation is to tailor the data products to the mission science goals. If the goal is to detect volatiles, you wouldn't want to provide a mineralogy map. However, you might want to provide volatile indicators such as a temperature map, or if you have the proper wavelengths selected, you could highlight where volatiles are actually present. Second is to consider a wider field of view. In our tests, we chose a narrow field of view due to the crew, which caused the crew to actually spend a lot of time thinking about where to select a sample or a scene for the HSI. And in some cases, the mental load of having to choose a site was kind of noticeable. So in these simulations, the narrow field of view was chosen to minimize the processing time in our short simulations. But in practice, a wider field of view would reduce crew workload and the mental load that they experience, and as well as streamline operations, and the processing of a flight instrument would be a lot more efficient than what we employed for these simulations. Our third recommendation is to have the support from a science evaluation room, or SER. In these simulations, it was just the crew, two-member crew, making the decisions based off of the HSI data. However, an SER could help with data interpretation in real time, providing direction to the crew on which samples to investigate in more detail, or which materials the crew had seen before at other sites, or which are completely new. Lastly, a pre-EVA reconnaissance with the rover could help make the EVAs more efficient and enhance HSI data. And to expand on that a little bit, next slide. HSI also has important applications beyond real-time decision-making during an EVA. A rover-mounted HSI, for example, could document a site before and after crew activity, helping to assess how the human presence alters the volatile signatures or surface composition. It could also map the mineral diversity across a wide range of areas and characterize inaccessible targets like crater walls and outcrops. And additionally, if you choose the white wavelength range, HSI can map volatiles such as water, sulfur dioxide, and methane, which we are all very interested in for human exploration, providing information about their abundance, storage, and the contamination of human activity. Next slide. This is just my so this is my conclusion slide. I just said all of this. I'm just going to leave it up until my time runs out. So thank you.